All right, so let's start our webinar. So hello everyone and happy Monday to all of you. If this is your first time to join our NRW webinar series, hello and a warm welcome to you. And for those who attended the previous webinar about Introduction to NRW with Ryan Paul Bacolinaw, thank you so much for coming back and joining us once again on the second leg of our free three-part live webinar on non-revenue water strategies from the specialists. So again, here I am. I am Karen Samante, and I'm the co-founder and digital operations and marketing manager of AJA Marketplace. And again, I will be your host for today. But before we proceed, let us go through our webinar guidelines. So if you will notice, you don't have the microphone or the video or camera functions on your Zoom right now. It is because we are in a webinar mode. However, if you have questions, you may raise that later on our or during our Q&A session. You will see there at the bottom part of your Zoom wherein you see all the other functions or menu, you will see Q&A button. So just click on that and type in your question and you will address that later during the question and answer portion. So please refrain from asking questions which are not related to the topic. And also, please be informed that this webinar is recorded. So later on, we will share with you the copy of of this webinar so that you can watch the replay. Also, the presentation slides and the Q&A, which will not be, or I mean, answers to questions which will not be answered later. And I believe I told you last time that we will send you the first part of the webinar. However, we just had some technical issues with the blast email. But don't worry, because if you will visit our website, aja-marketplace.com, we have assigned there. Let me check here. All right, so you will see here a link or a part which says webinar. Just click on this webinar. You will see on the drop down webinar videos, and it will bring you to this page wherein you can play the video, you can download the presentation deck, as well as the answers to the questions not addressed during the last webinar. All right, so again, just visit aja-marketplace.com. So also, if you'll be able to finish all the three parts of this webinar, we will send you a digital downloadable copy of your certificate of appreciation or certificate of participation. So please be advised that this presentation or the presentation proper will be 45 minutes. And after that, we will have a short break. After the break, we will proceed to the 15-minute question and answer part. So again, questions which will not be entertained because of the restrictions or limit with the time, we will try to address that via email. All right, so this presentation is brought to you or presented to you by AJA Marketplace. AJA Marketplace is a multi-vendor online website where you can request for quotation from different manufacturers, suppliers, and distributors here and abroad. So if you're familiar with Alibaba or with Shopee, that is actually the best way to explain what this marketplace is. However, this is more focused with the water and wastewater related products and services. Also, in the same platform, authorizers can proceed into checkout or ordering, also with the purchase order. So we believe that this will really be beneficial, especially for the end users and also the purchasing team, because it will make their procurement process more convenient. So if you want to register, registration is for free for customers. Just visit aja-marketplace.com. So let me also acknowledge, together with us today, let me acknowledge the presence of our CEO and co-founder of AJA Marketplace. He's also the one who initiated the webinar we are conducting right now. So Mr. Alan Gedang. So also this webinar is in cooperation with Philippine Water Works Association, or PWWA, Philippine Associations of Water Districts, or PAWAD, and the Water Environment Association of the Philippines. And of course, in special participation with the water loss specialists from International Water Association, or IWA. So now let me introduce to you our speaker for today. So he graduated from Portsmouth University in 1991 with a Master of Engineering degree in Civil Engineering. So he also has 30 years experience in the water industry, with 26 of those years whilst working in Southeast Asia. So during this period, he gained member status of the CIWEM in UK and is a chartered engineer. He has also gained a graduate diploma in international operational management and is the current secretary of the IWA Water Loss Specialist Group. He started his career as a network modeling engineer for Bywater International, and through this, he built up an expertise in how water supply systems operate. He then moved to NRW Management with Thames Water International and Ranhill Water Systems, gaining further expertise in leakage control, DMZ design and implementation, system monitoring, customer metering, and production metering. Also, he established the APAC Regional Office for I2O Water, specialist in advanced pressure management, where he was the APAC Managing Director for 4 years. He further improved his experience of pressure management whilst managing the regional office for Singer Valves, a manufacturer of pressure control valves. And currently, he is the Managing Director of Wyeth Water Consultants, a Malaysian brand or a Malaysian-based NRW management company. So you have already heard a lot, about him and his expertise in the non-revenue water, also with our topic today, the flow and pressure data management. So let me call on Mr. Gary Wyeth.
Thank you very much, Karen. Let me just start my screen. Okay, so good afternoon, everybody. Thank you for joining this webinar. And as Karen mentioned, we're going to be talking about flow and pressure data management. Last week when Ryan did his webinar, he was talking a lot about the IWA water balance, and a lot of the information that we need to put into that water balance comes from this flow and pressure data management. And also we can take information out of that water balance and use it to manage our non-revenue water levels. So let's start with the definition of non-revenue water. I hope that most people understand this definition. It's basically the volume of water produced. So this is the volume of water which is coming from your water treatment plants minus the volume of water billed. So this is the volume of water from all of your customer meters. So if you add up every month all of your customer metered consumption and you subtract it from the volume of water which has come from your water treatment plants, that's going to give you the volume of non-revenue water. And when we're looking at non-revenue water, it can cover the entirety of your water supply system. So starting at your water treatment plants, you can have errors in your production meters, and we're going to talk a bit about that now. Then it moves into distribution, where you have reservoirs, booster pumps, leakage in your pipelines. And then it moves on to the sales side, or the customer metering, where quite often we can have a lot of losses in our accuracy of our customer meters, the errors in reading those meters and then sending out bills. Typically, when we're looking at our losses, we would look at the losses in the distribution side would be physical losses, because we're actually seeing the water physically flowing away. And on the sales side, they would be what we call apparent or commercial losses. So they're more looking at losses in revenue, in money terms, rather than physical water loss. Now, hopefully everybody who attended Ryan's presentation last week will have seen the water balance, the IWA water balance. And it starts off on the left-hand side here with the system input volume. So this is your water treatment plants, the volume of water coming from your water treatment plants. Then we have your revenue water. So this is all of the water that is being recorded from your customer meters. And that then gives us a volume of non-revenue water. So this is the amount of water which you are treating, but you're not getting money for. And that non-revenue water can be broken down into a number of different components that we are looking at here. But generally, those can be split again, as I've mentioned, to be the physical or real losses and the apparent or commercial losses. So let's start with flow monitoring. And one of the key things that we need to be flow or monitoring of flows is, as I've already mentioned, is the flow coming from your water treatment plants. If you're not logging or measuring the flow from your water treatment plants, then you really can't start to calculate your non-revenue water. It's one of the key components of calculating the volume of revenue water that you have. So for all of your water treatment plants, you need to be looking to see how many outlets there are from the plant, how many pipelines are being fed from the plant, either under gravity or under piping lines. And you need to be installing some production meters that are actually measuring that flow rate. You can see here an example on the right, which is actually an electromagnetic production meter. We'll talk a bit in a minute about different meter types, but the electromagnetic meters are probably the most accurate flow meters that you can get. So if you are looking at measuring your production, you need to consider that you probably haven't got too many treatment plants and not too many metered outlets are required. So it might be somewhere around 10 to 20 of these meters. So purchasing some good quality, accurate meters is probably a good thing to do at the beginning. And as you only have a small number of them, then for this case, then the electromagnetics would be good. Another good option is ultrasonic flow meters. We generally have two types of ultrasonic flow meters. We have the strap-on types, which you can see here, where we have two sensors and we have a strap which is holding them onto the pipe. And what they do is they send an ultrasonic sound across the pipe and it comes back. And it actually measures a deflection in the sound wave to measure the flow rate. You can get some other ultrasonics where they're not strapped on, but you actually drill holes into the pipe wall and you can insert the transducers into the pipe themselves. Both have some benefits and some negatives as well. With these ultrasonic meters, one of the big benefits with them is going to be cost, because you can probably appreciate that it doesn't really matter what the pipe diameter is, whether it's 300 millimeter, 500, or even 1 meter diameter. The cost of the meter itself is pretty much the same. They don't get more expensive as they get bigger, unlike the electromagnetic meters. These are full bore, so you would need to cut the pipe and insert the meter in. And obviously, as they get bigger, the meter price itself gets more expensive, and also the installation costs get greater as well. Whereas for ultrasonics, you're really going to be almost the same price no matter what the pipe diameter is. So what does it look like in accuracy terms? And I think Ryan showed this table last week. And I mean, these are just indicative accuracy ranges. If you actually speak to different meter manufacturers, they'll probably give you the true accuracy ranges. But a lot of your meter manufacturers, they have their accuracies, and those accuracies are actually calculated on big test rigs that they have in their factories. So when you put them out in the field, there's going to be a number of different issues that can actually affect the accuracy, including things like pipe material, temperature of the water, straight length of pipes. So don't always believe what the manufacturers say. There's going to be some leeway in what the accuracy is really going to be. But you can see here that the electromagnetic flow meters are probably going to be the most accurate. But if you look at the ultrasonics, you can see that there's still a relatively good accuracy, which is between 0.5 and 1%. So whichever one of these you choose, you're going to be below 1% accuracy of your production metering. There are a few other metering options, insertion probes, mechanical meters and such, which you could look at depends on the cost side of it. But with the mechanical meters, they're really more for small diameters. So if you have some production pipelines from your treatment plant that are maybe less than 300 millimeter in size, then maybe mechanical meters could be an option. Insertion probes, they look good, but a lot depends on the installation itself and the team that's doing it. And then they do require maintenance over time to make sure that you're not losing the accuracy from the initial installation. So whichever you choose, it's important that you have something on your production meters, because if you just have a bare pipeline with no measurement at all, then it's really going to affect the accuracy of your water balance, and then ultimately your non-revenue water calculation. But once you've put the meters in, as I've mentioned, they do need maintenance. That you can't just put the meters in and then just forget about them. Some of the manufacturers do have some calibration software, which you can connect the meter up to a laptop and do some calibration. Really, they're only calibrating the electronics. So you may have to do some validation of the flow rate as well. So you can do drop tests. For example, if there's a reservoir, if the meter is coming out of a reservoir or flowing into a reservoir, you can actually close the outlet of the reservoir or close the inlet, and you measure a drop in the reservoir level, and then you compare that volume to what's gone through the flow meter. So that would give you an idea of whether you've got the volumetrics. You could also use an insertion probe. We've already talked about them. So if you were to install an insertion probe just downstream of your production meters, then you could compare the insertion probe with these meters. You're not going to get exactly the same flows because there's different accuracies from the different metering technologies, but at least you know if you're in the right ballpark within 2 to 4% of there. If you're out by 20%, then you know there's obviously an issue. Now, some water utilities, they actually buy their water, so they don't operate the treatment plant themselves, but they actually either buy water from a third-party treatment company, or they can buy it from a neighboring water district. If you're buying water from somebody, it's even more critical that you're measuring your production more accurately as well, because that's affecting how much you're paying for the raw water or the treated input water that's coming into your system. You can see an example here. This is actually one in Malaysia where they've installed 2 meters in series. So the idea is that if one of these meters was to fail, the second meter, the backup, would actually record, still be recording, so that they're not going to be losing any flow monitoring. This was very critical to them because the treatment plant was actually operated by a third-party operator, and they were paying for the water that was coming into the pipeline. Now, with these transmitters, which is the devices that come with your flow meter here, it actually has a flow rate on there, and it will have a totalizer telling you the total volume of water. If you want, you can just keep that totalizer and have somebody go out and read the meter, read the totalizer, either on a daily basis, monthly, if at the worst. Sometimes they have people go out and read them on a daily basis, so that you're getting the daily flows that are coming from the plant. The other option, which is often used by a lot of people, is to use data loggers or a SCADA system. So you actually have communication from the meter here. You're actually logging the flow rates, and then it's sending the data off to a control room or control center. That can be in the treatment plant itself, or it can be a control center in the water utilities offices. And that way you're actually going to get flow patterns, not just totalizers, not just volumes over a time period, but you're actually going to get flow patterns, and you can see when water is being used more or less than other periods. The other key metered component is our customer metering. And you can see in the water balance here, we've got 2 components. One is your billed metered, and we also have something called unbilled metered. So billed metered is obviously everybody who has a meter, and at the end of or during each month, the meter reader comes around and reads their meter, and then they get a bill. The second one is customers that have got meters on, but for some reason we don't actually bill them. This could be a decision that's been made by the local government or federal government, which is maybe people like churches or military camps, those sort of thing. They may have a meter, but politically you can't bill them. So there's an option in there. But we should make sure that even though we're not billing them, we should make sure that we're metering them so that we know how much water they are consuming. If we look at the commercial losses, because this is when we're looking at the metering, the customer metering side, any errors that we've got there, it's what we call commercial losses, because not only does it affect your non-revenue water, but it actually reduces the revenue coming to the utility. So if you can maximize the efficiency of your customer meters and the billing side, you're actually going to maximize your revenue that's coming in to the utility. So all utilities will have an existing volume of commercial losses, which is symbolized by this green box here. And then we also have what we would call an economic target of commercial losses. So economic target means that we're weighing up how much we're spending, and we would be spending on things like meter replacement, meter billing technology, meter reading technology. And then on the other side, we have the weighing up of how much revenue we would get. So there's going to be an economic target that we want to aim for. We're not going to be able to get it down to 0, but we want to get it down roughly to that economic target. And what do we need to work on that can help affect that? Well, we have meter under registration. So this is your customer meters that are no longer accurate. Hopefully, when you put a new meter into the ground or you install it on a customer's pipework, it's going to be fairly accurate. But over time, the accuracy of that meter will start to reduce as the meter wears and gets tear from just performance of the meter. So you need to be deciding, when do I need to replace those meters once the accuracy gets too low. We have theft of water. So something that's quite important in some countries is people that steal water. This is not something we're going to be looking at today, but it can be a large portion of your water losses, or it can be a small portion, depending on how big a problem it is in your utility. Then we have meter reading errors. So how do we go about and read the meters? Then how do we issue the bills to the customers? And I'll talk a bit about that in another slide coming up. And then the last one is water accounting errors. So once we've read the meters, and we then need to put those meter readings into a database, a customer database, before we issue the bills. So I'm sure most people have used Excel before, and they've typed in the wrong number into an Excel sheet and wondered why there's errors coming up. Well, if you have a system where you've got thousands of numbers that need to be inputted, then you can see where we could have errors that are occurring. So we're looking to resolve all of those 4 issues. And if we can resolve all 4 issues, we can actually reduce the existing commercial losses, and we can then move it down to that economic target. So this just shows you the accuracy of a typical customer meter, a mechanical meter. You can see that we have the accuracy, which is this pink line. So for normal flow rates, you can see that it's between 2 and -2. So it's a range of accuracy between 2 and -2%. But as the flow gets lower, we have what we call the QT, Q transition. So there's a flow rate point where it gets to QT, where the accuracy suddenly decreases. And you can see here that it goes to ±5%. The blue line that you can see here is a typical brand new meter. So when a meter is brand new, during the normal flow rate range from Qmax to QT, the accuracy is roughly around ±1%. But then once it gets to QT, the accuracy will then start to drop off. The red line shows you an older meter. So this is going to be an older meter, and you can see that over time, the meter is worn out. So even at the beginning, at the higher flow rates, we're already outside of the accuracy of a new meter, but you can see that that accuracy drops off. So even before we get to QT, we're already outside of the meter accuracy that we would be seeing. But roughly when should we be looking at replacing our customer meters? It's a very difficult question to answer. You can see here, this was some testing that was done. I think it was South Africa. And you can see here that they're looking at meters that as they age, so after 5, 10, 15, 20 years, you can see that the accuracy is dropping off. And it's quite, from the analysis they did, it's almost a straight line that you can see from the different data sets that were coming out. After 20 years, it's very difficult, or after 25 years, it's very difficult to predict what the accuracy of the meters are doing because they're just so worn away. But what we're looking at is that 0 to 20 year period. And for most utilities, what we should be looking at is the cost of replacing a meter and the revenue that's being lost. So if you were to say that we've got by year 7 or year 8, we've got a 2% additional error. So over 12 months, that's going to be 24% of the bill. And then we compare it to the cost of a meter. You'll probably find that most utilities, it becomes cost beneficial to be replacing meters somewhere between 7 and 10 years. But of course, that also depends a lot on the meters themselves. I've seen some very poor quality meters where this line drops drastically. So even after about 6 years, you've got very inaccurate meters. But also, you can get some meters that are a lot flatter as well if you have some very good manufactured meters as well. So it depends on the meter quality and who the manufacturer of the meter, but also a bit on the water quality as well, because if you have more sediments in the water, that can also affect how long the meter will last. I think what we're really trying to say here is the cheapest meters are not always the best. You can go out for a tender and you'll have some cheap meters that come in, but those meters may only last maybe 5 years. Whereas you might go for a more expensive meter and you've got a meter that would last maybe 10 to 15 years. So you need to be looking at the cost differential to see how long you think they're going to last and what the cost per year is, and see what's the benefit that way. So replacing your meters, it's always good to be replacing them with some good quality meters. Generally, when we're looking at our residential customer meters, we want to be using some mechanical meters. There's generally 2 types, which is the multi-jet types and also the piston types. This is a piston type, which is a bit more compact. Both are fairly good. The multi-jet types are more better for water systems that have poorer water quality or more sediments in them. Whereas these piston types, the sediments can actually get trapped in the workings of the meter and can actually wear it down faster. So generally with these piston types, we use them more in better quality water systems. But both of them should be good enough for any water utilities that we're looking at. There are a few more advanced ones that are out in the market now. There's a lot of electronic meters now. And also either electromagnetic or ultrasonic ones. With the electronic function, they actually have a lot more functionality where they can actually log hourly demands. They can give you alerts if they think there's a leak inside the customer's property as well. So if you're looking to upgrade from just the basic metering type, then maybe some of the electronic meters would be an option. A lot of water utilities are also looking at electromagnetic meters for the larger diameter customers. So if you're looking at your revenues that are coming in from your customers, and I don't know if any of you have heard of the Pareto law, which is basically that 20% of your customers will equate to 80% of your revenue. I'm not quite sure if that's true with water utilities, but you will find that if you were to add up your top industrial and commercial customers, the amount of revenue that's coming from them will be a high percentage of the revenue for the water utility. So what people want to do is they want to make sure that those large customers, the high demand customers, have got the most accurate flow meters and that you're measuring them to get the most revenue from them. So using an electromagnetic flow meter could be the best thing to do, is to start with the largest customers. Maybe not the largest in diameter, but largest in volume, because you want to get the maximum revenue coming in. I've worked on a number of projects where we've replaced the old mechanical meters with these electromagnetics, and the billing revenue goes up from somewhere between 10 and 15%. So the payback from installing electromagnetic meters on large customers is very quick. It's a matter of months. Now, billing, I mentioned about the billing side of things, and the very basic way is that you have a meter reader, and the meter reader goes out and has a piece of paper. He writes down the meter reading. That the table then goes back to the water utility, where somebody types it into the billing database. Then the bills get printed and the bills get sent out to the customers. When you're using that basic system, there are so many ways that errors can creep in. The meter reader can actually read it wrongly. He can type it wrongly or write it wrongly. Then when it gets back to the office, someone can type it in wrongly, and then the other errors that can happen when you start printing the bills as well. Now, one of the most common ways that water utilities are now getting around that is to do what we call spot billing. So spot billing, you can see in the picture here, the meter reader has actually got a handheld device. It's an electronic device. And what he does is when he gets to the meter, he types in the meter reading. And the handheld device has actually got the last 3 to 6 readings in the device. So when he types in the meter reading, the handheld device automatically does a bit of a calculation to see if it's roughly in the right ballpark. So if the customer last month, the bill was 500 pesos. The month before was 450 pesos. The month before was 480. And this month it's 470. The handheld device will let it go. But if suddenly the the reading puts in and the bill is now up to 2,000 pesos, then this handheld device will actually give the meter reader a warning to say, please input the number again, or please check the number. Once the meter reader puts in the right number or is happy that what he's put in is correct, he presses a button and the bill gets printed on the spot at the customer's house. He then tears off the bill and can hand it to the customer or post it in the customer's letterbox. That way, you're actually knocking out quite a large number of errors that could happen, especially with the meter reading part and then the typing into the billing database. The way you would still have a billing database, but when the meter reader gets back to his office in the evening, he puts the device into a stand and all of the readings will be sucked into your billing database so that you've got records of it all. Then, of course, you have the automatic meter reading. Now, I mean, I've got a picture here which is showing a typical AMR system, but it could be something simple like I mentioned before about your large customer meters, and that you could put on some electromagnetic meters onto your large customers. But you could also put a data logger, a flow logger onto that meter so that you're recording the flow that's coming from that meter, and that you can have the data sent back to your office on a daily basis. That means is if anything happens to the meter, let's say the meter was to break or fail, if you're only reading the meters every month, so 30 days, every 30 days, if that meter was to fail after 5 days after the meter reader has read it, you've then got 25 days with no data being recorded by the flow meter. And it would be very difficult to argue with the customer when you go back to them and try to give them an estimate reading. So if you have a data logger on there that is recording, and if you then, it would then pick up that something has happened with the flow meter, you could quickly get out there and replace it very quickly to make sure that you're not losing any revenue. You also have typically AMR systems, and you can see one here. They are generally used a lot for high-rise buildings. So if you have a high-rise building with many customer meters in that building, rather than have the meter reader going up and down the building, reading all of the meters, what you can do is have the devices sending their data back to a central unit in the building itself. And then that unit, either the meter reader goes and gets the data from that unit, or that unit can have a communication device, maybe a 3G or GPRS, and it then sends it automatically to your billing offices. This is obviously a lot more advanced than a lot of water utilities generally look at when they're beginning to manage their non-revenue water. But as you get more and more advanced and your non-revenue water gets lower and lower, so you're making more profits, you can actually start to invest some of that profit and revenue into more advanced technologies such as an AMR system. So that's the flow metering on the water balance side of things. But we're also looking at district metering as well. So if we look at the typical water supply that we looked at earlier, which is coming from the treatment plant, it goes through some transmission or trunk mains into service reservoirs, and then into the distribution network, and then into your commercial side. You actually find that a lot of problems that water utilities face is actually physical losses in your distribution network. And you can see here that it's actually a large part of the system. And that can be down to, in general, the fact that you have hundreds of kilometers of damaged and leaking pipes due to the poor quality of the pipe, the age of the pipe, the pressures in the pipe as well. So we really, one of the key things that we want to be managing is the non-revenue water in these distribution networks. But because it's so large, you can have a water utility that's got a huge distribution network. And that network, you may have something like 30, 40, or even 50% non-revenue water of leakage in that distribution network. And it can be very difficult to actually pinpoint where the problems are. And this is where we can actually use district metering into place. So if you look here, we've got a large distribution system on the left here with lots of open pipework. And we can actually break that down into a number of DMAs, district metering areas. And you can see that large area, we've broken it down into 10 plus DMAs. So these are like smaller zones that are individually isolated. Before we have DMAs, it's very difficult, as I mentioned, to actually identify where the actual leakage problems are, because we're only measuring flow at the treatment plant and your customer meters. You just get a general overview of the non-revenue water. And when you have leakage teams, they don't know where to go. So basically you're just sending them out in a hope that they're going to find some leaks, which they do sometimes, but a lot of times they may not find any leaks or the proper leaks. And so this then makes the leakage teams a bit demoralized because they don't see any benefit from what they're doing, because the non-revenue water levels are not really dropping. But once we do get our district metering areas in, the DMAs in there, we can actually install some flow meters. So you can see a DMA here, and it's because it's isolated. If we install a flow meter here, we know that all of the flow going into this DMA has to go through this meter. So if we put a pressure logger, a flow logger onto this meter, we can actually measure the flow going into this DMA. We can also use data loggers that have GPRS or 3G communication as well. So these data loggers record the flow and pressure as well from the flow meter, and then they send the data back via GPRS or 3G on a daily basis back to our control rooms, so that we can analyze the DMAs to work out what the leakage volumes look like. And this is what we're looking at. We're actually looking at a typical daily flow pattern going into a DMA. So you can see that we have the flow at night is low, and that's generally true because at nighttime, most of our residential customers are asleep in their beds. Most commercial customers are shut as well. All of the shops, supermarkets, they tend to be closed or using minimal flow. And it's only really some industrial customers that are actually operating at nighttime. Then during the day, we have the peaks in the morning, and then we have an evening peak, and then it drops down at night. Because most of our customers are not using water at night, we can actually use this night flow as an indicator of our leakage in our systems. So we call the flow that we look at night, we call it minimum night flow, or MNF. And you can see here we've got some indicators of what that minimum night flow is. But it's not truly what the leakage levels are, because as I mentioned, there are some customers that are still using a bit of water at night. There may be some industry, maybe some hotels, or even some people that are awake using water. So what we have to do is we then have to subtract the legitimate night flow. So this is the customer use at night. We subtract it from the minimum night flow, and we come up with what we call net night flow. To do that, of course, we need to know this legitimate night flow. And how do we do that? Well, we have our staff actually going out on site reading the customer meters. So they need to go out on site at night and read the customer meters during a certain period, so that we can actually calculate what is the legitimate night flow. And we have some pretty standard forms that can be used. You can see in this one, we're actually reading, what we do is we read the customer meters at 3 time steps. So you've got time here, 1, time 2, time 3. And it's up to you what times you want to use. You could be doing midnight, 1 a.m., 2 a.m. Or you could do 1 a.m., 2 a.m., 3 a.m. As long as you're getting a period during that nighttime period when you're going to be measuring the lowest flow. Now, you don't want to be measuring every single customer. So if you have, let's say in this DMA, we have it's a housing area, and we have 1,000 properties. You don't want to have people going out reading 1,000 meters every hour. So what we actually do is we read a sample. So for example, if you have 1,000 DMAs, you might read 50 of those 1,000. And then what we do is we use that as an average, and then we just multiply by 20 to get the total legitimate flow for all of the residential housing. For some of the other metering types, like commercial and industrial, if there's not so many of them, sometimes you may only have 10, 20, 30 of those per DMA. Then it's important that you actually read all of them. because they can all be quite different in the amount of water that they're using. And then from that, you can then calculate the total legitimate flow for that DMA. And then if you know what the minimum night flow is, you can then calculate the net night flow. Another factor that you need to consider is what we call the T factor. So this is the pressure, your pressure in the zone over 24 hours. Because with pressure, pressure is actually inversely proportional to flow. So at nighttime, when you have your lowest flow, you are actually going to have your highest pressures. So that means you are going to have higher leakage levels at night because you've got higher pressures. In the daytime, when the flow picks up, your pressures will drop, and that means your leakage volumes will drop as well. So looking at your net night flows at night will not necessarily indicate to you what the true leakage is over the 24 hours. So we do something called a T factor pressure testing. And what we do is we actually measure pressure across a DMA, and we do it here in 2-hourly intervals to give the highest and the lowest over that 2-hour period. And we then have got the average pressure every 2 hours. And then what we do is we create a leakage index. And if you look at this one here, you can see that the T factor is actually 22.4. Now, if it was on a par with the leakage at night, it would be 24 hours. So because the pressure has dropped during the day, the leakage is actually dropped. So it would be 22.4. If the pressure actually went up during the day, then you would actually see a figure here above 24 hours. So to get your true figure of leakage, what you do is you take your net night flow, you divide by 24, and then you multiply by this T factor to get the true net night flow figure for that DMA. And this is what we're looking for. We're actually looking at those minimum night flows or net night flows, and we're seeing that what we want to do is we want to see the net night flow remain fairly stable. If we suddenly get a jump up, as you can see here, it's jumped from 10 to 13, then that would indicate that something has maybe happened. We wouldn't automatically send the leakage teams out after day 1 because we want to see what happens on day 2 and possibly day 3 as well, to see whether that leak is consistently there. Once we've got to day 2, we might say to ourselves, okay, there's something that has definitely happened and it's maintained. So we would need to send our leakage teams out to go and investigate. Once they go out, hopefully they can find a leak that's caused that 3 liters per second drop. And then hopefully we can then go out, we can repair the leak, and you can see that the night line will drop down, and it's dropped down here to below 8 liters per second, which is a good way of controlling the non-revenue water in your DMAs. But of course, not all leaks are large. So you're not going to see a jump from 10 liters per second up to 13 liters per second in one night. What often happens is we just get small leaks, and we get lots of small leaks that are occurring all over the place. And you can see here, this is a plot of the net night flow over a long period of time. It's actually months. So that's 1 month, 2, 3, 4 months, 4.5 months to here. So from here, you can see the night line was below 4 liters per second. And gradually the night line has crept up until it's above 15 liters per second. It's at this point that the utility says, okay, we need to go in and do leak repairs. So they've done some leak detection, they've done repairs, and it's come back down to 4 liters per second. But you can see that it's gradually creeping up again. So there's one of the key things that you need to be looking at from DMA to DMA is what is that intervention level? What level of net night flow do I find acceptable? It could be that you set it at 5. You could set it at 10, or you could set it at 15. It just depends on the time interval here. So 4 months to go from 4 to 15, maybe they could bring it down to 10, so that after 2 months they could go in and break it down. So the intervention level would depend a lot on the water utility itself, how many staff you have to go out and do leak detection, and how much of a problem you see the leakage level rising from 5 to 10 to 15. And this just shows you over a long term what we would see it happening. The night flows would actually keep rising up and up until you hit that intervention limit. Then you would do leak detection and repair, drop it down. Then you would see that level increasing again. Then you would do leak detection, repair, and then you'd see it going up again. And it's a continuous program of continually monitoring the night flows, seeing them gradually increase until it hits that intervention limit. And of course, the intervention limit, as I mentioned, can be adjustable. So you can adjust it over time, either up or down, depending on the situation that you're in. This is showing you what can happen if you have huge numbers of DMA. So you can see for this utility, they've got 743 DMAs or DMZs. It's the same thing. And what they've done is they've actually categorized them into different net night flow levels. So they've got from less than 2.5 liters per second up to greater than 40 liters per second. You'll see here that there's also what we call unreadable. This can be a problem with the flow meter itself or the data logger that's sending the data back. I do know, because this was a project I worked on, and this was over 15 years ago, that at the time we used to use not mobile phones, but we used landlines to communicate with. And we used to have a huge problem with lightning strikes. So when you had lightning in an area, it would hit the telephone lines and it would run down the telephone line and the modem would blow up. So that's why we had quite a few unreadables. But what we're really concentrating on is this net night flow. You can see, obviously, the ones that are above 40, in fact, above 20, are key critical ones. These could be brand new DMAs that have only just been set up and we need to bring them down for the first time. Or they could be a DMA which is in a very poor condition. So we may have DMAs that have got very bad pipes in very weak. I know that some DMAs where we used to find 30 leaks every month, we'd repair them, but the night line never went down. And we go back the month after and find another 30 leaks. And the month after we find another 30 leaks. And when that happens, it's basically time for you to do pipe replacement. You can see that on this diagram. It's a bit complicated, but you can see here, the night line is increasing. And then the utility says, okay, that's enough. We're going to drop it down. They've even set the intervention limit here because they felt that this was too short a period. But now it's rising up and it hits the intervention again. And so they're doing repairs. But you can see the time period between leak detection and repair activities is getting shorter and shorter. And this is telling you that your pipe network is just too weak for you to be continually doing leak detection and repair. So the next step is to move and do either pipe rehabilitation or pipe replacement. Generally in Asia, people do pipe replacement. Rehabilitation is not something which is done on a large scale here at the moment. pipe replacement is done. And you can see now that there's a much slower increase in the rate of rise. And it means that we can put the intervention limit a lot lower as well. Now, when we're looking at the night lines, which gives us a leakage volume, that's not the only bit of data that we can get from our non-revenue water data we can get from our information. So we can start off with actually total non-revenue water volume. So we have here the volume of water. If you have a DMA and you have your flow meter on the inlet to the DMA, you're actually going to measure the volume of water going into that DMA in a 1 month period. If you've also got all of your customer meters and you read them every month, you've got the consumption. So if you take the volume in minus the consumption, you've got your total NRW volume. And you can see here that we can list out those total NRW volumes. And straight away, we can start to look at which DMAs have got bigger problems. You can see this one is very low, this one's very low. So those two, maybe not ones on our priority list. But if we look here, and you can see there's 1 and 2 very high ones. We then look at the night lines, so that net night flow. So if we can work out what the net night flow is, let's say it's 4 or 5 liters per second, we can then work out what that is over a monthly to give you your monthly volume. And we've now got the leakage volume here. And once again, we've got some that have got very low leakage and others that have got higher leakage. So if we've got non-revenue water and we've got leakage, the other one is the apparent losses, the commercial losses. So if we just take the non-revenue and we subtract the leakage, we now have our apparent or commercial losses. And if we go down here, we can now see the DMAs that have the highest commercial losses. So we could look at this, for example, and say, okay, this DMA has got the highest non-revenue water, but if you look at that non-revenue water, most of it is actually commercial. We do have quite a bit of leakage, so we definitely need to send our leakage teams in there, but we also have a lot of commercial losses. So doing some meter replacement in that area or going out and checking the meters would be, hopefully, would help us to increase our revenue as well as reducing our non-revenue water. We can use also an indicator called ILI, which will also help to show us which DMAs have got the worst leakage problem. So you can see here that the ones in red have got the highest ILIs, and they would be the key ones that we would be looking at to sort out on the leakage side of things. But you can see this one has a very high ILI, but the volume of leakage is actually less than some of the others, but the ILI is high because it's a very high percentage of the NRW volume. So creating a table like this just basically helps you to start to prioritize where you need to be sending out your leak detection teams and also your commercial teams to work out whether there's meter replacement plans that are needed for individual DMAs. So with your DMAs, you're basically looking to prioritize your leak detection and repair, especially if you have a large number of DMAs. Any pipe rehabilitation or pipe replacement works. This can help you to identify which DMAs need that pipe replacement. And also customer meter replacement, which DMAs you think would benefit from replacement of some of the customer meters. And this then helps you to reduce your NRW, gives you greater efficiency, stronger pipe network, and improved revenue. So we're now going to move lastly onto pressure monitoring. We've already talked a bit about pressures when we were looking at the T factor and looking at DMAs, but we're going to look at specific monitoring now. And probably one of the key areas for a lot of utilities is reservoir level monitoring. So this is actually measuring the pressure level in your tanks, or the level of water in the tanks. You can go for a very basic data logger where you just have a pressure sensor on the outlet pipe, and the logger is recording that pressure and it sends the data back on a daily basis. Or you could go for a more complicated SCADA system, which we've got here, which is online. So you've got a continuous feed of what's happening to the level in the tank. Whichever way you go for, what we're really looking for is to identify where we're getting leaks coming from tanks, or more critical is overflows from tanks. Now, you can see here that when we've got the recordings of the level of water in the tank, if we get flat lines at the top water level, that's indicating that there was some overflow because the water got to that top level and then you were losing water and it was just a flat line. So by having some sort of monitoring, we're actually picking up these overflow activities. One of the things is that, as we've noticed, you have low flow at night because your customers are not using the water. This means that the water flowing into your reservoirs is actually filling the reservoirs up at night rather than flowing out to the customers. So quite often when reservoirs start to overflow, it's in the middle of the night, between 2 and 4 in the morning. And if we don't have any staff around, or if you don't have any customers around, especially if the reservoir is in a remote location, then you may not have an indication that it's overflowing at all. So by having some sort of level system on your tanks, you're actually going to be able to identify those issues quickly so that you can resolve them. The other pressure management that we can do is actually in the DMA. So we've already talked about having a DMA, and you've got a flow meter going in to the DMA so that we're measuring flow in. But we can also use a pressure reducing valve to control pressure in each individual DMA. And when we're using pressure reducing valves, it's very critical to consider two different pressure points. We have what we call an AZP. This is your average zonal pressure, which is the average pressure point in your DMA. But we also have what we call a critical point. This is your lowest pressure point in the DMA. And that can be either an end point at the end of the DMA, or it can be at the highest point on a hill somewhere. But somewhere in your DMA, you're going to have a critical point. And it's very important that you're logging the pressure at this critical point, especially when you're doing pressure management programs using a PRV. And this is just showing you what happens. You've got your pressure upstream, and then you've got your pressure after the PRV. So the PRV is knocking the pressure down. But then what happens is, over your DMA, you're going to get head loss due to the flow going through, friction of the flow going through your pipes. So at the end of your pipe network, you have your minimum pressure, your lowest pressure at the critical point. So you can see here that the pressure has dropped from 60 down to 20 meters due to frictional head loss across the DMA. But friction is actually created by flow. So at nighttime, when we have that low flow, you can actually see the pressure going up. So you can see here that there's almost no head loss at night. So we've got a pressure at the end here of 60 meters. So your critical point, the pressure at your critical point is going to be changing over a 24-hour period. And if you're going to be setting the PRV up, you actually need to know what the pressure is doing at the peak flow, because that's when you want to be setting your PRV so that you don't have too low a pressure during the peak demand period. And this is what you would actually see happening. You've got the outlet of the PRV is the line in blue. And then the pressure at your critical point is the green line. So at nighttime, you've got high pressure. And then at night, you've got the, during the daytime, you've got your lower pressures. So it is quite variable. Now, with your PRVs, you actually want to control the pressure. And the reason why we want to control that pressure is to reduce the leakage. And there's a very good relationship between pressure and leakage, and it's a square root function. So basically, if you reduce pressure by 10%, you're going to reduce your leakage by 10%. So for example, if your system had 50 meters pressure and you reduce it down to 40 meters, that means you've reduced your pressure by 20%, and your leakage volume would then reduce by 20% as well. Similarly, if you only have very low pressures, maybe you've got only 10 meters pressure and you reduce it down to 8 meters, you've also reduced it by 20%, and your leakage volume would reduce by 20% as well. So pressure management is something that can be done not just when you have very high pressures, but also at low pressures. You can see small adjustments in your pressure can have a big impact on the leakage volumes. Now, with your PRVs, as we've mentioned, with a basic PRV, you can actually see pressure being high at night because you've set your PRV to give you a pressure at the critical point at the peak demand. So with all PRVs, you can actually put on some controllers. So controllers can go onto your PRVs to control the pressure. The one I'm showing here is a very simple on-off pressure, or high and low pressure. So you have high during the day for 6 hours, then you have low at night, you have low in the middle of the day, and then you have high in the evening, and then it goes back to low at night. So this can be done with a very simple timer system that's controlling your PRV to go from high to low. Moving on from that, you can actually have more advanced controllers that also measure the flow. So what they do is, as the flow goes down, they drop the pressure. And as the flow comes up, they increase the pressure. So they're a lot more advanced in controlling the pressure and giving you a much more stable pressure at your critical point. So that is really how we look at pressures. We look at the levels in your reservoirs, and then we're looking at the pressures in your DMAs that we want to control, because we want to control leakage levels, leakage volumes in your distribution areas. So I think that's the end of my presentation, and hopefully that's given you a good idea of what we want to do in terms of managing or monitoring your flows around your network and using them to manage your activities, and then your pressures as well to actually reduce your physical losses. Thank you.
All right, thank you so much for that, Gary. And on behalf of everyone here today, thank you for taking time to speak to us. And as what Gary said, there are a lot of factors affecting like commercial losses, for example. And I appreciate how Gary emphasized the issues which leads to commercial losses. And I believe these are really something that should be considered while coming up with short-term or especially with long-term water management strategies to increase revenue and decrease NRW. Also, it is important to have knowledge on different flow meter and also be updated on the new technology available for meter reading and customer billing, because it is true that you cannot really control what you cannot measure, right? So accurate and active flow measurement, as well as the right equipment to use, is very important. So once again, thank you so much, Gary, for the information-filled presentation. But please do not leave us yet. Also, for all the attendees, we have around like 298 attendees now. So just stay, and we'll have a short break. Come up with the questions that you want to ask. Just put it on the question or Q&A button that you will see. So we will be back around, let's say, 3:20, and then we will proceed with the question and answer.